What could be this thing you're currently looking at? Just a simple sand simulation, right? What if I told you it's a real-time simulation running purely within SQL? Everything, the physics, the simulation loop, the rendering state, and even a secret mechanic, all purely using SQL. Well, if you're interested by now, keep watching and enjoy my suffering as I try to implement this completely useless but kinda satisfying project. Oh, and if you find yourself enjoying this, maybe consider liking, subscribing, or even leaving a comment. Now, every good idea, starts with an equally good set of parameters. I don't want this physics engine-ish thing to be a gimmick, so not a one-off query, but something consistent that runs at a decent enough frame rate, with real-time updates, a nice visual interface. Yes, that one is not SQL. My fault for not wanting to look at ASCII characters moving in my console for days on end. And even time travel. Now, we know SQL has some noteworthy properties. It's deterministic, it's transactional, it's extremely good at bulk operations, and it really doesn't want to behave like a game loop. The first fork in the road was pretty straightforward. How do you represent a 2D world inside Postgres? If you've ever built a grid sim the normal way, your brain probably reaches for the obvious schema, which is a cells table with a bunch of properties like the x index, y index, whether it's solid, sand, or empty, and so on, which you have to index, so it helps a bit when you have to update rows each frame. And to be fair, that does work. It's also the fastest possible route to discovering that you just built a physics engine out of the slowest kind of workload a relational database can do. Tiny random updates to lots of rows many times per second. Even if the grid isn't huge, let's say a 256 by 144, that's still more than 36,000 cells. If each tick needs a handful of updates per cell, or even just a subset, you quickly end up with something that's less real-time and more like compulsively watching paint dry. So the pivot was, don't store the grids as rows, store them as bits. A Postgres bigint is 64 bits. If you treat each bit as a cell, one bigint represents 64 horizontal cells. So for a width of 256, you would need 4 bigints per row. For a height of 144, you do need 144 rows. From there, the project's core pattern became: keep exactly one authoritative state row in sim state, lock it per tick, update arrays in memory inside the function, and then write the updated arrays back in one update. But this bitwise shift also implied creating my own SIMD-ish instruction set. So that was fun. But hey, my early suffering allowed present me to run this stuff at like 20 FPS without issue. Now, sand sims are generally way simpler compared to fluid sims. A normal full-fledged fluid sim, in Navier-Stokes style, implies stuff like velocity fields, diffusion, pressure projection, advection, all of it stuff that sounds cool in theory, but it would realistically evaporate any chance of a real-time sim in SQL, which may or may not be a reason for which I spared myself from implementing one in SQL. But that doesn't mean I am happy with that basic 1980s limited physics stuff. So who is to say I can't bring some stuff from the fluid sims into my little sand sim to make it move more like actual sand? But now the simulation tick evolved into a pipeline like this. First you have the gravity, which is a vertical fall. Then you have diagonals, meaning falling around obstacles, and finally you have a lateral flow for spreading and filling. Each pass is essentially first compute where the sand wants to go using bit masks, then apply moves using bitwise operations, and finally maintain emptiness masks as you go. I first compute empty grid once at the start of the tick. Then when the sand moves, I update both the source row's emptiness, it becomes more empty, and the target row's emptiness, it becomes less empty, so I don't have to recompute full grid emptiness repeatedly. This way I can avoid additional whole grid scans and keep the tick cost much more stable. Okay, first off, if you compress gravity into one idea, it becomes: if there's water at xy and empty at xy-1, it should fall. In bit terms for a row, it would look like this, and the update would look like this. Secondly, sand, or fluids likewise, in the context of a cellular sim, look fake if it only falls straight down and spreads sideways. Diagonals are what let it flow around corners and stack naturally. Bitwise diagonal moves require shifts. Down left means the destination cell is one bit to the left in the below row, so you have to test the emptiness by shifting the below emptiness mask opposite direction to align it with the source row. And for that final oomph that gives more of that fluid feel, lateral flow. My initial version had a single lateral move per tick. It worked, but you could tell it was very robotic and limited. Piles would be filling really slowly and spreading looked really chunky, and also there was a lot of jitter at the surface. This is where the biggest improvement came in: lateral micro steps. Instead of one lateral pass per tick, you run, let's say, 2 to 4 mini passes. Same logic, just repeated. That does two things: dunes feel faster and they feel more like sand, and surface movement smooths out because you effectively allow a sand cell to travel multiple cells per tick in aggregate. The cost is linear, but because every pass is still bitwise, for smaller dimension it's still a good trade-off. But even with micro steps, cellular sand can look indecisive, like it can't commit to a direction. Real sand tends to continue flowing in the direction it already had. So I added momentum, but in a way that stays pretty cheap. You have a momentum left grid with bits marking sand cells that prefer left, and a momentum right grid with bits marking sand cells that prefer right. Then, in the lateral flow step, you move momentum aligned sand first, and then you move the rest. When sand moves left, you set or preserve momentum left at the destination. Similar for right. And over time, you just decay momentum by randomly clearing some bits so it doesn't become permanent. The final big thing was leveling. A cellular sim tends to produce jagged surfaces unless you do extra work. So, to counter that, I opted for surface-only flow passes. They pretty much go like this: you define surface sand as this, and then you do extra lateral microsteps only for those bits. This means the sim spends extra effort moving the stuff that visually matters most, the surface layer, which gives it that feeling of pressure. Well, now I have the building blocks for the sim, so naturally you'd think it's just smooth sailing from here on out. Well, the reason more games aren't implemented in SQL, just one singular reason, of course. Databases don't really do game loops. They are transactional engine. Game loops are persistent processes. Trying to force one to be the other is how you get ghost states, random locks, race conditions, and a gallery of bugs that would belong in a natural history museum. So here comes the part where I bend the rules. Just the tiniest bit. I'm letting Node do the time, because the crime is in the process of being committed. The final architecture was having Postgres own the state and the step function, and the web server calling SimStep at a fixed interval. The web client polls or subscribes for the latest frame. This way I could have the whole thing be stable. Postgres operates with short-lived function calls, locking a row, computing, updating, and then committing, while the Node server just does the infinite loop plus the timer, the things it's actually built for. But I'll come back to Node in a second. Now let's talk time travel. Not actually time travel, but what about rewinding and branching out? Those are two things that would generally be a headache to implement. But when your language of choice is SQL, with its inbuilt rollback mechanism, it would have been a crime not to do it. For my simple rewind system, every tick I insert the send grid into a history table keyed by tick, and when I want to rewind, I copy a historical frame back into the sim state. So now I have sim state for the current real-time simulation and sim frame for the archive. Each row in sim frame stores the arrays for that tick, and later momentum too. This makes rewind instantaneous. However, if you store every frame forever, prepare to fork over some cache, cause your database will need some new shiny storage, and a lot of it. So I added a retention window, using a keep frames variable in state, which makes it so that each tick, frames older than tick minus keep frames, are deleted. It's pretty much a rolling buffer. The only caveat is that rewind can only happen after the sim is over. So you can play out your sim, stop it, rewind to wherever you want, and play from there. Otherwise, you get an old-fashioned race condition. Now, if the simulation's stable, the web app was all about making this feel like an interactive project, which is funnily enough done by delegating as little work as possible to the client. No computation, no simulation. Everything needs to be done by the database to stay as deterministic as possible. In the back, it's just two loops, one for querying for SimStep and the other for broadcasting events via WebSockets. Other than that, it's just endpoints that map the SQL functionalities to REST APIs. The input doesn't depend on tick timing beyond locking, so you can click away as fast as possible. Those are all atomic updates on the database, which are then serialized with the SimTick. So, sick of SQL talk already? Or maybe on the contrary, motivated to see what this language that clearly wants to be more than what people say it is can actually do and push to its limits? I think I got a pretty good idea of its potential, and dare to say managed to make quite a pretty cool real-time simulation, wouldn't you agree?